Welcome to day 4 of the advent of compiler optimizations. We're graduating from addition, and today we're going to be looking at multiplication, at least multiplication with a constant. So over here in Compiler Explorer, I have a multiply with a constant function, and I'm going to start and return x, first of all, so we know that that is literally just going to move the input into the output. And if I scroll up, you can actually see it. So in this instance, returning a value multiplied by nothing at all gives us, well, no multiply at all, gives us EDI, the input value, being moved straight into EAX, the return value. If we multiply with 1, you can see the compiler just completely ignores us. For integers, that doesn't do anything. So it knows that it can still just get away with the move. What happens if we multiply by 2? Have a think before I change the code and see if you can guess what's going to happen. It's an LEA. There's no multiply at all. It's actually an add. Multiplying by 2 is the same as adding x to itself, and multiplies are relatively more expensive on CPUs than additions. So wherever possible, the compiler will try and use additions. So here we're saying that LEA should be equal to RDI plus RDI. So we get a multiply by 2. What about by 3? Surely we're going to get a multiply now. So for a multiply by 3, what we see is an LEA. So all roads seem to lead to LEA. In this instance, what we're using is LEA's ability to have a base register plus an offset register multiplied by 1, 2, 4, or 8. And here we're using the identity x plus x times 2 is the same as 3x. So here, RDI plus RDI times 2 is the same as RDI times 3. Fantastic, we've still avoided an actual multiply. Moving to 4, yeah, it's still an LEA. LEA 0 offset plus RDI times 4. So here we're using a 0 offset, no register and no constant offset, plus RDI times 4 to just get 4 times RDI. And it'll come as no surprise that multiplying by 8 also gives us an LEA instruction with RDI times 8. We know it can do 1, 2, 4, or 8. What about some things in between? 5. Again, 5 is an LEA because we can add ourselves with RDI times 4 and we get a multiply by 5. 6. Well, now something more complicated had to happen. We do a multiply by 3 and then we add ourselves to ourselves. So here we're using an LEA to do the multiply by 3 and then we're adding EAX to itself to get multiply by 6. So the compiler is pretty smart here. It knows all these tricks and whatnot. Let's try something a little bit more complicated. Let's pick 25 out of nowhere. 25 apparently, so let's work this one out. That first line is RDI plus RDI times 4. That is multiplying by 5, and then, oh, it's doing the same again. So we're multiplying by 5, and then we're multiplying by 5 again, without actually using a multiply, using adds and shifts, which is what was going on inside that LEA instruction. Now, surely there has to be a limit. Surely at some point we give up. So let's just pick another random number, 522. Yes, the compiler runs out of tricks at 522. Or probably way before that. But 522 is an example of a value which has no obvious way of breaking it down into shifts and adds. And so the compiler uses an IMUL instruction. The IMUL instruction here is one of the rare examples of an x86 instruction which does in fact have a separate destination operand. So here, IMUL EAX EDI 522 allows us to multiply EDI by 522 and put the result in EAX all in one go, which is pretty cool. If, like me, you're a bit of an old school hacker and you're used to doing multiplies with shifts and adds, you might be looking at that 522 and going, wait a second, 522 is 512 plus 10, 512 is a power of 2, 10 is 8 plus 2, and 8 plus 2 are also powers of 2. So it's only 3 powers of 2 which are shifts and adds. Why don't we try building it ourselves and see if we can beat the compiler? So how would that look? We want x shifted up by 9. 9 would be 512, so this is 512, plus x shifted up by, let's think about it, 2, 4, 8, 3. That gives me my 8, plus x shifted up by 1, which is to multiply by 2. So this is x times 512, x times 8, x times 2, and then we're going to compile that and see what the compiler generates. So the compiler can see through my shifts and adds and has replaced it back with a multiply instruction again. So what's happened? Turns out the compiler is smarter than me, which is of no surprise to most people who know me. The compiler knows that multiplies are fast these days, relatively fast, and certainly faster than the equivalent shifts and adds that I was asking it to do. So it's backed out the fact that these shifts and adds amount to a multiply with 522, and it's just replaced it with that multiply and saved me from myself. Now, if we were to change back to using Pentium or something really old, so let's do that. I'm going to go back into here and I'm going to do -M32, which puts into 32-bit mode, march equals Pentium. Now, the ABI has changed a bit, so bear with me on that. But here we can see now it is using shifts and adds to generate the multiply. So maybe that's better. Except the compiler still knows more. And in fact, if we just write the multiply x with 522 and get rid of all the stupid things that I was doing here, it generates much better code than I was generating. It just does some shifts and adds appropriately. So the moral of the story is, if you tell the compiler which architecture you're targeting, it will do the right thing. You don't have to think about this anymore. There's no need to be writing return x shifted up by 9 anymore. Just return x times 512 or whatever. The compiler has got your back. So, moral of the story is, trust the compiler, and hopefully I'll see you tomorrow.